All right. Hi, class. So we have a midterm in a week, and I just want to let you know that I'm going to make an announcement about that as usual. So if you have questions, I would ask that you wait until you see the announcement first. Working on it as fast as I can. I'm going to try a slightly different way of writing my notes, which is I'm trying writing some of them before class and then writing more by hand. So I'm going to see how this works out. So as you can see, today we're talking about hypothesis testing. We're going to finally learn about the famous p-value that maybe you've heard about or seen statisticians make reference to. Well, after today, you're going to know what it means. So our goal today, here's the goal. We're going to collect data, as if from some sample. And we're going to have a hypothesis, and we're going to determine if the data either supports or detracts from that hypothesis. We're going to try to determine if the data provides enough evidence to reject our so-called null hypothesis. And I'm going to explain what these terms mean shortly. In favor of some alternative. And the way this is usually going to work is, okay, you collect some data, and you want to know if there is an effect. I don't know, does taking Adderall increase test scores? But you assume the opposite. The null hypothesis usually is that there is no effect. But usually you want there to be an effect, because that's a bit more interesting, that's more statistically significant. So you kind of want to reject the null hypothesis. So there's 4 steps in hypothesis testing. Sorry, hold on a second. Crap. Sorry, I'm a little bit distracted. I made some edits to this this OneNote page, but apparently they didn't sync with my laptop yet, so it's throwing me off a little bit. But okay, I can deal with it. Deal with the unexpected. All right, here we go. So step 1 in hypothesis testing is, well, you create your... What? Okay, right. All right, so step 1, create your hypothesis. There's actually 2 of them, the null hypothesis and the alternative. You're going to state a so-called null hypothesis. And we're going to use, as typical, H sub 0, or H naught, as it's called. And an alternative hypothesis. H sub A for alternative. So how about let me illustrate this with some examples. How about if you have a friend that claims that he has a coin that's unfair, like maybe it lands on heads more, maybe it lands on tails more. I'm not going to say, we're not saying which side it favors, but let's say you have a friend who claims this coin is unfair. So you want to determine if a coin is fair or not. To do so, how about you flip it a bunch of times and you let P be the proportion of heads that come up. Now, as I said, the null hypothesis is like the boring one. It's that there's no effect. It's that we see just what you would expect to see, which in this case, the null hypothesis would be that it is a fair coin, and you just get heads half the time. The alternative hypothesis is that it's not fair, which is that the proportion of heads is not 1/2. This is what is known as a two-sided hypothesis test, because the alternative, it could be that it's unfair in favor of heads, or it could be that the coin is unfair in favor of tails. We're not saying that. We're not saying which one in the alternative. So there's two ways that the alternative could go, making this what we call a two-sided hypothesis test. I'm also going to show you an example of one-sided tests, and it's kind of tricky to figure out which one to use. That's going to be one of the confusing parts to figure out today. So here's an example with a two-sided test. Sorry, I just did two-sided. Here's an example with a one-sided test. So how about Purdue Pharma or pharmaceuticals? Purdue Pharmaceuticals has been in the news for the last couple years because they were the makers of OxyContin. There's a lot of blame on them for the current opiate epidemic, because they were the company that was aggressively marketing OxyContin back in the day and telling doctors that it was not very addictive. So Purdue Pharma claims that less than 5% of OxyContin patients become dependent on the medication. Supposing that if P is the proportion of patients that become dependent, then we can phrase this as a one-sided hypothesis test as follows. So you could make your null hypothesis that it is 5% that become dependent, but the alternative, which is what Purdue claims, is that it's less than 5% that become dependent on the medication. So here we've got a one-sided hypothesis test. Or here's a related example. There's a big lawsuit against Purdue Pharmaceuticals. Yes? For the purpose, that's the assumption. So, okay, there are more complicated ways you can make hypothesis testing. We're starting off with the most basic, simple ones for now. Yeah. So, sorry?
I thought null hypothesis would be like have to be like if it's less than 5% and the alternative would be retesting.
There are multiple ways you can set these questions up. This example is meant to illustrate the one-sidedness of the hypothesis testing, and I could maybe rephrase this example as, let's say the accepted rate of medication dependence is 5%. Purdue claims they've got a new pill that's less than 5. Okay, that maybe I should have written that in this question to make it more clear as to like what the null effect is versus the alternative. Yes. Well, we're testing Purdue's claim that they're producing patients with less than 5% addiction rate. But you could phrase the question differently. So here would be a similar example. How about in the class action lawsuit that's going against Purdue? Claims that the proportion of OxyContin patients who become dependent is, let's say they're claiming that it's greater than half. In the lawsuit, let's say they claim that more than half the people that try this drug become dependent on it. So in this case, we're exploring the hypothesis that the proportion who become dependent is greater than 1/2. So contrast that with the null hypothesis that it's equal to 1/2. This would again be one-sided because of the alternative hypothesis is that it's simply greater than a number. You could go either way, right? Yeah. And as far as you're concerned, like above is just as likely as below. So that's going to have the effect of cutting probabilities in half, as we shall see. And I do an example in the second half of class today. Now, whether you use a one-sided hypothesis or a two-sided hypothesis test, it depends on what you're interested in the question. It's not a mathematical question, though. In this case, if you were suing Purdue, it would be bad for your lawsuit if the true percentage was less than 50. Like, you want it to be more than 50. So that's the side of the hypothesis that you're interested in, hence the one-sidedness of your hypothesis. And similarly, if you're Purdue, you want it to be smaller than 5%, not more. Having set up your hypotheses, the next step is to calculate a test statistic. And the test statistic, it should reflect the extent to which the data is consistent with the null hypothesis versus the alternative hypothesis. Exactly what test statistic you calculate is going to depend on the problem. It'll depend on the model. It'll depend on the alternative hypothesis. But basically, you want to see, like, how unusual would it be to observe the data that you observed given the null hypothesis that you're supposing. Next, you calculate a p-value. That's a probability. It's the probability of observing data as extreme. And by extreme, so here's where the alternative hypothesis comes into play. Extreme means in favor of the alternative hypothesis. Okay, so that's the p-value. P-values are kind of tricky, but they are important. And if you think about, when you have some sample and you get like a sample proportion, obviously the sample proportion is not going to exactly equal the population proportion. But whatever we do get for the sample proportion, we want to ask the question, okay, so like how likely was it that we should get such an extreme value given the null hypothesis? Like, let's say you tested some sample. Like, I ask, first row, what's your average age? And I asked, Viet and, wait, how do you say your name again? Nelia, yeah, and you guys, and I came up with, like 80 years old. Well, that's way more than the average. So that seems like if I assume that the average age in the class is about 19, that would put that hypothesis into question, very much so. Finally, we write our conclusion based on the p-value that we get. And the conclusion, there's two possibilities. We either accept or, we either reject the null hypothesis or we fail to reject the null hypothesis. The what? Really? Yeah, I heard all that yelling. Oh. Huh. Yeah, good. I guess I'm off their mailing list because I'm not a grad student anymore. Good. Oh, okay. So, wonder if the TAs are doing section and stuff. Man, we got to find some scabs, some strike breakers, man. Wonder how much they'd pay me to be a TA today. Or not to be a TA today. Yeah, go to the highest bidder. Okay. Cool. So, we either reject our null hypothesis or we fail to reject it. I like this fail to reject the null hypothesis. There's a lot of double negatives going on in that sentence. Right? It's like we're not saying no to the possibility that nothing is happening, right? Yeah, that's what it means. We're not saying something's happening, right? And we're not saying nothing's happening. We're just not saying that it's not true that nothing's happening. So yeah, it's weird. So it's kind of like a trial. In a jury trial, when you go to trial, the jury can find you guilty, or they may not find you guilty. In order for a jury to find you guilty, they need to be sure that you are guilty beyond a reasonable doubt. Right? That's the standard of evidence. So that's like what we're looking for if we reject the null hypothesis. That means we are sure beyond a reasonable doubt that the null hypothesis is false. If you can't establish that burden of proof, then you can't convict, right? If the hypothesis don't fit, you must acquit. Just made that up. Okay. But does getting, okay, so if you are not convicted, does that mean you're innocent? Not necessarily. It just means they didn't have enough evidence to convict you. So that's the deal with hypothesis testing. We're not saying the null hypothesis is true. At no point during this section do we ever say that. We just can't reject it. Okay, so, and typically, so like how do we know whether to reject it? Here's how. It'll mostly vary case to case, but here's a typical circumstance. Typically, we reject H0, the null hypothesis, if the p-value falls below our alpha threshold. Below our significance level. Right, so alpha depends on the context, but what's our usual significance level? 0.05 is the standard one. Yes, so usually alpha is 0.05, and without any other information, you can usually assume that it's 0.05. Okay, so it's like when our p-value is small, that means that observing what we observed given the null hypothesis was very unlikely. So we probably reject. A small p-value means we probably reject the null hypothesis, meaning there's probably an effect. A large p-value means there maybe is not much going on, and we can't reject the null hypothesis. Cool. Okay, so I can do my example now.
So does rejecting the null hypothesis is that prove the alternative hypothesis?
The language would be we reject it in favor of the alternative hypothesis. So it supports the alternative. Yes? That's a judgment call. It's super unlikely that it would land right on that point. So, okay, I came up with an example involving involving birth months. So I used the class survey data involving, well, what months you were all born in. And I'm going to make this question about October babies, okay? Yeah. So we had 19 October babies in 150 respondents to the class survey. Is that a fluke, or is something going on in January that results in a bunch of October babies? Well, actually, okay, so I'm going to phrase the question very carefully. Here's the question I'm asking about October. I'm asking whether, dang it, I edited this question and it is not reflecting my edits. Okay, sorry, I'm gonna I don't know if it's because I'm out of Wi-Fi here. Let me slightly modify this question just to make it more clear. The hypothesis is that 1/12 of babies are born in October, okay? 1/12 of births occur in October. Which is the, okay, so what's the null hypothesis? Is that, yeah, it's a 12th of all the babies born are in October, same as any other month, that there's nothing special going on. Now, as written, what's the alternative? Yeah, Rachel? Okay, could be more, although as written, so that's a question to ask. As written here, though, I'm just questioning whether it's a 12th or not. So I'm not saying there's more or less. It looks like there's more, indeed, and we can ask that question. But as written here, I'm just trying to find out whether it's a 12th or not. Okay, which means that as written, this is a two-sided question. So let's, to form our answer, let's follow the various steps. The first step was to create a hypothesis. So we're going to let P equal 1/12. That's the hypothesized proportion of births that occur in October. Then our hypothesis, the null hypothesis, which is to say that there's nothing special going on with October, sorry, yeah, hold on. Sorry, let me go back a couple steps. So we are asking whether 1/12 of babies are born in October or not. The null hypothesis is that the proportion of babies born in October is 1/12. The alternative hypothesis is that the proportion of babies born in October is not 1/12. And we have a sample of 150 students, but in general, we'll let p hat be our sample proportion. Now, if you assume the null hypothesis, well, then I have a sample, 150 students in this case. It seems pretty reasonable that births between different students would be independent. So in that case, it looks like we have a binomial distribution. Right, binomial of n and p, which is binomial distribution with 150 students and 1/12 probability. This binomial distribution satisfies the almost normal condition for binomial distributions, which is that np and nq are greater than 10. Because remember, we are assuming the whole way you set this up is you assume the null hypothesis is true. Assuming the null hypothesis is true, so NP is 150 times 1/12, which is 12.5. That is greater than or equal to 10. And n times 1 minus p is 150 times 11 over 12. That's also greater than or equal to 10. So the normal approximation is appropriate. And so the mean of this binomial, which is approximately normal distribution, is p. And the standard deviation of our sample statistic is, this is one of the formulas we were doing back when we were talking about central limit theorem and binomial distributions. It was p 1 minus p over n, which is, in this case, assuming the null hypothesis, 1/12 times 1 minus 1/12 over 150, which comes out to about 0.0226. Any questions? You have it?
So for conditions, you have to check independency, randomness, and normality, right? So then do we need to show proof for like independence and randomness? Because we can't, just because we can assume that it's independent because it's universe, and we know it was a simple random sample. So like, would we need to prove like mathematically randomness and independence?
No. Yeah, it's a fair question. And like in many of these, we're just going to assume. He was asking about independence and randomness, the conditions you, in general, should check. But yeah, it seems pretty reasonable in this question to assume independence and randomness, so we're just going to assume that. Okay, so yeah, Rachel? Because we want to do computations using the normal model. So you'll need the two parameters. I'm going to use that in a second right now, basically to get a z-score. So this one will remind you very much of a confidence interval. It's p-values and confidence intervals involve very similar looking calculations. Okay, so now similar to how I would calculate a confidence interval. By the way, one difference between this and a confidence interval you might notice is I have the actual standard deviation instead of, for sample proportions, I had to use the standard error, which was an approximation to the standard deviation. Here, for hypothesis testing, we've got something a bit better, which is the actual hypothesized standard deviation. So that's one difference between this and a confidence interval problem. So, but in both cases, we now standardize so we can do computations. I will standardize by using the letter z. So, right, so I'll let z equal p hat minus p over the standard deviation of p hat. So z is approximately a standard normal. And there's a name actually for that, by the way. So z is our test statistic. And it's also called a z statistic. Okay, for our sample, we have a value for p hat. Right, an actual observation of what the sample proportion was, and it was 19 out of 150, which is about 0.1267. By the way, p, which we are supposing is 1/12, is about 0.0833, by the way. So the observed z statistic is approximately 0.1267 minus 0.0833 over 0.0226, which is about 1.92. So we observed a proportion of October babies that was 1.92 standard deviations above the mean. 1.92 standard deviations above what we would expect. How unusual is this? So the p-value is the probability of observing data that's this extreme, given the null hypothesis. And remember, by extreme, we mean in favor of the alternative. We got data that was 1.92 standard deviations from the mean. Anything that's more than 1.92 standard deviations from the mean is even more in favor of the alternative hypothesis. So that's why I'm going to include all the area that's 1.96 standard deviations or more. So let me get out a z-score calculator here. Okay, well, I already did it because I prepared beforehand, but here's the z-score calculation. Oh wait, oops, I did the wrong number there. Let me do the, okay, I did not do it beforehand. Here's the calculation. 1.92 was our z-score. Okay. Oops. Okay, so what I'm trying to say is I want all the data that is 1.92 or more. In other words, I'm caring about this picture right here. This is the probability that I'm interested in. It can be 1.92 on the right or 1.2 on the left because we're doing the two-sided hypothesis test. Thus, the probability that my test statistic is greater than or equal to 1.92 is about 0.055, and that's my p-value. Okay, so let me try and say this in a sentence. If birth months were evenly distributed, and if October was just as likely to be your birth month as any other month, then suppose I collected many groups of 150 people. And in each one of those groups, I counted up the number of October babies. In 5.5% of those groups, the proportion of October babies would be 1.92 standard deviations away from the mean. In other words, so the mean, the expected number in 150 people we would expect 1/12 of 150, which is 12.5 October babies. Um, 19 is 6.5 extra babies. So in many groups of 150 people, 5.5% of the groups should have either more than or equal to 19 or less than or equal to 6 October babies. Oh, in fact, so here, I'll show you the actual distribution of birth months from the class survey data that was up here. So you can see we were looking at October, which was the highest point. Interestingly, there actually was another month where we got, where this event that supposedly only happened 5.5% of the time happened, and that was in April, where there was only 6 April babies. So it seems like more than 5.5%, because in this yes, that, how should I say this? Well, no, because there's also other months as well. So there were plenty of possibilities. I'm not going to do the actual math on that because I don't have time. Yeah? Good. Yes, exactly. So that's what I need to get to right now. So do we reject it or not? What's our conclusion? Well, what do you think? What did I say the cutoff, or like the standard cutoff was? 5%, good. And we got 5.5%. So yeah, we're not going to reject it. We fail to reject. Because, yeah, 5.5%, it wasn't rare enough for us. But what if I modified the question a little bit? What if now, using the same data, what if now I propose that something's going on in the winter months? I don't know what. Maybe like weather's cold and couples are bundled up like indoors under the comforter or something. For whatever reason, there's a lot of October babies. So if I proposed a different test, if I proposed that the alternative hypothesis is that there's more than the standard ratio of 1/12 of October babies, and the null hypothesis is that there's no effect in October. Can anyone tell me what the p-value for this hypothesis test is? Wow, you guys are good, man. You already do the homework? See? Nice, okay, way to go. Yeah, all right, so Viet said it, but I'll say it again. So the question is, should we reject this hypothesis? Now, so I'm running low on time, but I'll just tell you the p-value here is 1/2 of what it was before, which is about 0.027. The p-value is exactly, I'll show you what we're looking at for this test, this area right here, okay? 0.027 is our p-value because this is a one-sided test. Should we reject this hypothesis? So this is a smaller p-value, meaning it would seem very unlikely to observe 19 October babies when we only expected 12.5, given that this is the alternative. Given how unlikely it is, and it's less than 5%, in this case, we do reject the null hypothesis, because it does seem like there's something going on in the warm months of January, or cold months of January. Yeah. And that there is some effect that results in more babies.